Chapter 2.5, Zeros of Polynomials. So in this chapter, we're going to talk about a lot of theorems. We have the rational zero theorem, the linear factorization theorem, and Descartes' rule of signs, all of which are going to help us to identify factors of our polynomials. So, to begin, we have the rational zero theorem. If the polynomial f of x equal to an x to the n plus an minus 1 x to the n minus 1 and so on down to a0. This is just generic polynomial, has integer coefficients, so no fractions or anything. Then every rational zero, rational meaning fractional, of f of x has the form p over q, where p is a factor of the constant term a0 and q is a factor of the leading coefficient an. When the leading coefficient is 1, the possible rational zeros are the factors of the constant term. So that last statement is going to be really helpful later on. An example of a question you could get using the rational zero theorem is simply list all possible rational zeros given a particular polynomial. So to do that, here are your steps. You're going to start by identifying what is a0 and what is an. So an in this case is 2 and a0 is negative 4. So here we have an, a0. An is always just the coefficient of the highest powered term, and a0 is always the constant. If there is no constant, a0 can just be 0. To find the factors of these, we just look at, now we have 2, we want to think about, well, what goes into 2? 2 is a prime number, so not much. 1 and 2 both go into it, but we want to think about the fact that negative 1 and negative 2 also are technically factors, because negative 1 times negative 2 equals positive 2. Similarly, for negative 4, we get positive and negative 4, positive and negative 2, and positive and negative 1. That's how it's always going to look for these types of problems, is remember that you have to write positive and negative next to everything, or else you will be marked wrong. Now, by the rational zero theorem, our possible rational zeros are anything that's of the form p over q, where p is a factor of a0, so these are going to be our p's, and q is a factor of an, so these are going to be our q's. So I just need to list out every possible combination of p over q. So that's 4 over 2, 4 over 1, 2 over 2, 2 over 1, 1 over 2, 1 over 1, and their positive and negative forms, like so. But notice that we have some repetition here. So for example, 2 over 2 and 1 over 1 are the same number. They both equal 1. So if we simplify this, we would eliminate any repetition because we don't need to state things twice, and we get positive negative 4, positive negative 2, positive negative 1, and positive negative 1/2. And those are all possible rational zeros. Note that not all of these are zeros. These are just the only possible ones. Again, rational ones. If there is a possibility of complex zeros or irrational zeros in certain problems, but we're talking about the rational zeros that we basically find through factoring. So these are the only possible options. So let's do another one. Find the zeros of f of x in 4x cubed minus 3x minus 1. Well, here it's a little bit of a deeper problem. Before, we were just looking for all possible zeros. Now we actually need to identify which ones are the actual zeros. So step 1, we can list out all possible zeros. So we use the rational zero theorem to list all possible rational zeros of the function. So that's going to be positive and negative 1, positive negative 1/2, and positive negative 1/4, because we have our an equals 4, our a0 equals 1, so we just want what are the factors of each. Factors of an are going to be 4, 2, 1, positive, negative, positive, negative, positive, negative. Factors of 1 are simply positive, negative 1. So combining that all together, we get positive, negative 1, positive, negative 1/2, and positive, negative 1/4. Then, our next step is to use synthetic division to evaluate the given possible zeros by synthetically dividing the candidate into the polynomial. If the remainder is 0, we found a 0. Otherwise, we didn't and we discard it. So in other words, now we do some guess and check, because that's all factoring is a lot of guess and check. But at least we have a nice method to see whether or not we guessed correctly. So, we can pick any random 0 we want. We can start with, for example, 1. And I will go through the steps here. So 1, and then 4, and 4, 0, negative 3, negative 1, and I bring down my 4. 4 times 1 is 4, 0 plus 4 is 4, 4 times 1 is 4, 4 minus 3 is 1, 1 times 1 is 1, and look, we found a 0. But let's try another one. How about negative 1? Well, 4, 0, 3, negative 1, bring down my 4, times negative 1 is negative 4, plus 0 is negative 4, times negative 1 is positive 4, add them, we get positive 7, times negative 1 is negative 7, and that's negative 8, so I discard that one. I know negative 1 is not a 0. And here I have shown negative 1/2 is a 0, so there's another one we can find. So once you find 1 0, you can continue the process. So once I get here, I can continue, and I would check a new number. I can multiply in, I can go 4 times 1, and then add in that negative 2, and then multiply, and then I get a 0, and I see that 1 is a 0, and so you can keep going this way, or you can convert it into quadratic factoring. So we can repeat step 2 using the quotient that was found with synthetic division, or if possible, continue until you get a quadratic and then factor the quadratic. So that is really up to you. Here I've shown how I can continue, and then essentially I've gotten down to where I need to be. At the end, I can't really go any further than this. But I can also use normal quadratic factoring to factor this 4x squared minus 2x minus 2 into a slightly nicer form. So in order to do that, I'm going to pull out a 2, and then I'm going to factor 2x squared minus x minus 1 into 2x plus 1 times x minus 1. So this is one way I can answer it. I can also rewrite the entire thing as 2x plus 1 squared times x minus 1. There's a lot of ways we can write this depending on how we want to present it. So if I multiply the 2 into this one, I would get that, and then I wouldn't have any fractions left, so that's a lot nicer to look at. Either way, remember that we talked about multiplicity before. So at this point, we can then state our zeros are at negative 1/2, because if I plug negative 1/2 in here, I get a 0. If I plug negative 1/2 in here, I get a 0. So it's negative 1/2 multiplicity 2, and 1 multiplicity 1. So either way you want to leave it, whether you leave it like this or like this, we're still getting negative 1/2 multiplicity 2 and 1 multiplicity 1. So this is just to sort of demonstrate that there's more than one way to present your final answer in a question like that, depending on how you got your zeros. Next, we have something that sounds pretty important, the fundamental theorem of algebra. So if you continue with mathematics into calculus and beyond, you will learn a few more fundamental theorems. Specifically, the fundamental theorem of calculus is focused on in calculus. There's a lot of different fundamental theorems out there for each subject, but the one for algebra is if f of x is a polynomial of degree n greater than 0, then f of x has at least one complex 0. So it may seem kind of odd that this is so fundamental to algebra, but it really is. There's just a lot more depth to it than is shown here. So we can use this theorem to argue that if f of x is a polynomial of degree n greater than 0, so basically any polynomial you're looking at, that's not a special case, and a is a non-zero real number, then f of x has exactly n linear factors when we have f of x written in the following way. So f of x equal to a times x minus c1 times x minus c2 times x minus cn, where the c's are complex numbers. Okay, so in other words, we're saying that we can always factor our polynomial down into linear factors, no matter what. So you may see a polynomial that looks like, let's say, for example, x squared plus 2x minus 1, right? Yeah. There's no way this is factorable. This function does not factor in real numbers. But with the use of complex numbers, we actually can factor it. I'm not going to ask you to necessarily factor that at this moment. We will talk about that later, but it involves the quadratic formula. So no matter what, even if this is not a factorable in the way you have learned it, polynomial, we now have a theorem that tells us that no matter what, you actually can factor it, as long as you now include our complex numbers. So, therefore, f of x always has n roots, or zeros, or solutions, or however you want to call it, when we count multiplicities. So if you remember back when we first introduced polynomials a couple chapters ago, I hinted that, well, the multiplicities of each of the factors added up to the degree of the polynomial, but that was only in particular cases. So that's not always true, at least not when we deal with only real factors. But as soon as we include our complex zeros, no matter what, if we count our multiplicities, it's always going to add up to the degree of our function. So remember that a complex number can be real or imaginary, or a combination of both. So just because I've written it as if there's a whole bunch of complex numbers, well, complex numbers can involve both, can involve I or not involve I. Now again, I'm sort of introducing complex numbers here without having really talked about them before. So if you don't remember how complex numbers work, I suggest going back and reviewing chapter 2.1 that covers complex numbers. It's not something we focus on here because, again, just like quadratic factoring, it is something that is covered in algebra. So if you're not familiar with it, then I suggest doing some review of that chapter. It will help. Or you will see some of it in the lab for extra review, etc. You can, of course, ask me, but I'm not going to go over it here. So you just have to kind of take my word for it here that complex numbers can involve real and imaginary numbers together, or separately, and imaginary numbers just mean there's an I in there. So hopefully that sparks some memory for some of you. So our next theorem then is the linear factorization theorem. So a polynomial function will have the same number of factors as its degree, and each factor will be in the form x minus c, where c is a complex number. So that's basically what I concluded the previous slide with, that any polynomial will have the exact number of factors as it has degree. So if we have x squared, it does factor into two things, even if it doesn't factor under the real numbers. If it has x cubed, it'll have 3 factors. If it's up to x to the 4th, it'll have 4 factors, and so on. We can use this statement to show that if the polynomial f has real coefficients and a complex zero of the form a plus bi, then the complex conjugate a minus bi is also a zero. So that is introducing a new concept that, again, is sort of covered in the complex numbers chapter that we're not talking at length about. So let's just go over this a little bit more in depth, though. Essentially, a complex conjugate, if we have a complex number, a plus bi, that's the way we state any complex number, 3 plus 5i, or negative 7 plus 2i, or 2 minus 3i, etc. Those are complex numbers. they could have no real part. We could just say minus 7i. They could have no imaginary part. It could just be the number 3. But either way, these are all complex numbers. The complex conjugate comes in when we simply switch the sign next to the I. That's all that happens. So the conjugate for 3 plus 5i is 3 minus 5i. The conjugate of negative 7 plus 2i is negative 7 minus 2i. Then 2 plus 3i. Then 7i. Then, well, for just 3, because remember these were separate, for just 3, it just stays 3. There is no complex conjugate if you don't have an imaginary term. So, here we have our complex conjugates. Essentially, I'm not going to go through why we can use the linear factorization theorem to prove this statement because it's a little bit more complicated. But we can use this theorem to tell us that if we have a 0 at 3 plus 5i, then we have a 0 at 3 minus 5i. If we have a 0 at negative 7i, then we have a 0 at positive 7i. But if we have a 0 at 3, we have a 0 at 3. Nothing changed there. It doesn't mean we have one at negative 3. We've seen plenty of examples where that wouldn't be true, so we know that isn't true. So this only works when you have that imaginary term. So let's apply this, though, to a kind of complicated problem. But we're going to use this fact to make it a bit simpler. So find a 4th degree polynomial with real coefficients that has zeros of negative 3, 2, and I, such that f of negative 2 equals 100. Alright, so this is a pretty long problem to do. First, we want to think about the fact that it says 4th degree. So that means it goes up to the x to the 4th. Okay? So our polynomial is going to look like f of x equals a 4x to the 4th plus a 3x cubed plus a squared x squared plus a to the 1st x to the 1st plus a 0. So that's what our end answer should look like. But we know from our linear factorization theorem that in factored form it should look something like a times x minus c1 times x minus c2 times x minus c3 times x minus c4. So we're kind of working our way backwards from a factored form. We have this factored form and we want to now plug into it. We know our zeros. Our zeros are negative 3, 2, and I, but we should have 4 of them. So that's where our complex conjugate comes in. So we're going to replace our c's with our zeros of negative 3, 2, and I, but we're also going to have to include negative I. So since I is a 0, negative I must be a 0 due to it being its complex conjugate. So we plug each of these in. We get x minus negative 3 is x plus 3, x minus 2, x minus I, and then x minus negative I, or x plus I. So at this point, we remember that it did state it wanted real coefficients. Essentially, it's just going to be a lot nicer to look at if we get rid of those i's, because that's generally how we look at a factored form of a polynomial. Is we don't look at it with i's. We don't think about that as its nice factored form. Instead, we want to look at it with just its real coefficients. So we're going to take x minus I times x plus I. So x minus I times x plus I is equal to, using our foiling, we get x squared, that's an I, not a 1, x squared plus ix minus ix minus I squared. So remember that I squared is actually equal to negative 1. That's how complex numbers, that's where complex numbers come from. That's how imaginary numbers work, is that I is the square root of negative 1. So I squared is negative 1. So our plus ix minus ix are going to cancel away, and we'll get x squared minus negative 1. So minus negative 1, or in other words, plus 1, like so. So essentially, that's how it should always work out. is we should always be able to get rid of those i's by doing that multiplication of our complex conjugates. That's why the conjugates are there, is because that's the only way to cancel out those i's, to get rid of all of the imaginary parts, is by using a conjugate. That's the purpose of the complex conjugate. So, once we have that, once we have simplified it to use x squared plus 1 instead, we can now apply the fact that we know f of negative 2 equals 100. In other words, we will substitute in that negative 2. So f of negative 2, we just plug in negative 2, and our goal is to find what a is, because that is the last thing we don't know, is what is a. So we leave our a, and we plug in negative 2. So it'll be negative 2 plus 5, negative 2 plus 3, which is negative 1. Then negative 2, no it isn't, it is positive 1, I apologize. Then negative 2 minus 2 is negative 4. Then negative 2 squared plus 1 is positive 4 plus 1 is 5. And so, altogether we have a times 1 times negative 4 times 5, which all of that is negative 20. So, f of negative 2 equals a times negative 20, which is equal to 100 is what we were told. So, a times negative 20 equals 100. Our final step is just to divide out that negative 20 to get a equals negative 5. So, once you get a, you have the factored form, you have a, we can state our final answer all together, where we replace a with negative 5 to get f of x equals negative 5, x plus 3, x minus 2, x squared plus 1. So we have the fully factored form, and then we can also write it out in its general form with each of the real coefficients. So we see there are no i's left, even though some of our zeros were i's. And that's basically how we can use our linear factorization theorem to solve a problem like this. Alright, so our last sort of theorem that we're going to look at is Descartes' rule of signs. So, this one is a little bit weird too. If we let f of x equal, again, a general polynomial, so a n x to the n down to a0, with real coefficients, so each of the an minus 1, all of that are real numbers now, the number of positive real zeros is equal to the number of sign changes of f of x, or is less than that number by an even integer. Now that's a lot. It's pretty abstract until you try it out, and then it's pretty easy to actually do, so bear with me for a moment. Similarly, the number of negative real zeros is either equal to the number of sign changes of f of negative x, or is less than that number by an even integer. Okay, so let's actually apply this, because just saying it out loud, I can't really explain it verbally so well, but seeing it is going to make a lot more sense. Will it make sense why it works this way? Unfortunately, no, because that's a bit deeper than we're going into. But, for example, a question you could be asked where you would have to use Descartes' rule of signs is, how many possible positive and negative zeros are on the following function? So, just like with the rational root theorem, in the rational root theorem, it was only asking what are the possible rational roots, not what are the actual ones. Descartes' rule of signs tells you what possible number of zeros you get. So we know the total number of zeros should be 4, right? Because by our linear factorization theorem, we know this is a 4th degree polynomial. It has 4 zeros if we include our complex numbers. But this allows us to sort out how many of them should be positive, how many should be negative. And by knowing that, we can also interpret how many should be complex. So, first, we're going to take this function, we're going to find f of negative x. So remember how to do that back when we talked about plugging in a negative x when we dealt with odd and even functions, etc. So, f of negative x, we are going to get changes of sign anytime our degree, or the degree of our term is odd. So hopefully you remember that pattern from dealing with the odd and even functions. So here when I plug in negative x, it is negative x to the fourth minus 3 times negative x cubed minus, or plus 6 times negative x squared minus 4 times negative x minus 12. Like, that is really what f of negative x is. But we can sort of quickly say, all right, the sign is only going to change if it is an odd term, because negative x cubed is negative x cubed, but negative x squared is positive x squared. So we get negative x to the fourth plus 3x cubed plus 6x squared, same sign for the x to the fourth, and same sign for our negative 12, of course. But we get a change in sign between our negative 3x cubed to our positive 3x cubed and our negative 4x to our positive 4x. Alright, so now we have f of x and f of negative x. Nothing really new or groundbreaking here. We've done that in our previous chapter, or our previous unit. Now, how do we apply Descartes' rule of signs once we have that? Well, essentially, our goal is to figure out how many changes of signs there are in each. And I don't mean the fact that we change signs between the negative 3x cubed and the positive 3x cubed. That's not what we're dealing with, because the number of possible positive real zeros is the number of sign changes in f of x. In other words, well, we start with negative x to the fourth, and then we move on to negative 3x cubed. Those are the same sign. They're both negative. Then we go to positive 6x squared. That's a change in sign. We went from negative 3 to positive 6. Then we go from positive 6 to negative 4. That's a change in sign. But we go from negative 4 to negative 12, and that's not a change in sign. So that tells me there were 2 sign changes in f of x. Similarly, there are 2 sign changes in f of negative x. It's not always going to be the same, but in this case it was. So we get so we can mark off each of our sign changes, and then we can state, okay, so there's 2 sign changes, which means we can now apply Descartes' rule of signs, that the positive real zeros are the possible number of positive real zeros has to be 2, or is less than the number of changes by an even integer. So in other words, we get the possible positive zeros are either going to be, this is again the count of them, how many there are, not the actual zeros themselves. So there's either going to be 2 positive real zeros or none, because I count down by 2's. Similarly, a number of possible negative zeros is 2 or 0, because I got 2 changes, and then I count down by 2. So I go 2, and then I go 0, and then negative 2 would be next, but you can't have a negative number of zeros. That wouldn't make sense. So altogether, we get the following table of options, because we know that the number of zeros, by the linear factorization theorem, has to add up to 4. We have to have 4 total zeros. So either we have 2 positives and 2 negatives and no imaginary zeros. We get 2 positives, no negatives, and 2 imaginary zeros. We get no positives, 2 negatives, and 2 imaginary zeros. Or finally, we actually have no positive and no negative, but 4 imaginary zeros. Those are all possible options that we could have. Now you'd have to go through, you can do your rational root theorem, to your synthetic division, etc., to actually factor this and see which of these is correct. From the way it looks right now, I can't tell you, but I can tell you possible options, which is really just there as a guideline to help you kind of see, should I be plugging in negative numbers or positive numbers to help? Like, that's the point of this, is to help you know, should I even bother plugging in positive numbers, or should I only try doing synthetic division with the negative options out of the rational root theorem, or something like that. Alright, so one last note to make here, because I know this is a point of confusion for a lot of people. Let's say I had a function, something like, let's say x to the 5th minus x to the 4th plus 3x cubed minus x squared plus, that's 1, 2, 3, 4, plus x minus 1. Okay. Clearly, there's a lot of sign changes here. We got 1, 2, 3, 4, and 5. So we got 5 sign changes, which would mean that my sign changes in f of x are 5. My sign changes in f of negative x are going to be different. I believe it might actually be none. Yeah, none. So when we have a larger number of sign changes, when we have an odd number of sign changes, I know that this can get a little bit confusing for some people. So the possible positive zeros, possible number of positive zeros is 5 or 3 or 1, like that. So when I say we count down, sorry if that color is vibrating a little bit, but we count down by 2s. So we had 5 changes, means we have either 5 zeros, 3 zeros, or 1 zero, and then we stop. So similarly, where we had possibly 2 zeros or no zeros, and then we stop. So there is not a possibility of no positive zeros here. There has to be at least one, because the next counting down by 2 would have been -1, and you can't have a negative 1 zeros. So again, these are numbers of zeros, not the actual zeros themselves. All right, so hopefully that clears up any confusion about that one. But essentially, that's it for this chapter, and that's it for our exploration of zeros in polynomials. Next, we will be going on to rational functions, which is going to take all of this stuff and sort of put it together and make graphing even more tricky. But it's still going to be a lot of fun, I think.